Okay, hello everyone and welcome to Berlin Machine Learning Meetup. So due to coronavirus, we have to have this meetup virtually, and it's actually good for me because I don't live in Berlin anymore, and because of that I have lost track and missed quite a lot of meetups. So I hope all of you are safe at home. And today we have 3 great talks. So if you want to ask questions, please ask in the chat box. We will moderate and select a few questions for the speakers. So just to start with, I will hand over to Trent, who is going to provide an introduction for the first of the speakers. So Trent.
Okay, hi everyone, can you hear me all? Yes? Okay, great. So, yeah, thanks everyone for joining us to the meetup. And I will start with the introduction for the first speaker. This is our very first virtual meetup ever, so we're a bit new to it all. So apologies for the lag and all that, but we're gonna practice and improve here. So we have 3 speakers tonight, and the first one is going to be speaking about how to classify news articles in the real world, and it's actually 2 speakers. We have Helena and Amankaya Peña from Upday, as well as Gosa, is that right? Close enough? Okay. And her last name is Adamczyk from As Ideas, and they're going to be basically, talking about how to classify news articles in the real world. Helena is a data scientist at Upday, which is a digital news company, and her drive is to work towards useful, human-friendly applications of data. She studied biomathematics and completed a PhD in math at the University of Greifswald, Germany. And then Gosa works as an ML researcher at Axel Springer in the AI unit of it. And previously, she was a member of the data science team at Idealo, and she's worked on projects in domains of natural language processing, computer vision, and she's currently exploring the potential of GANs for image generation. So yes, welcome and thanks for speaking. Off to you guys.
Thank you for the introduction.
Hello, everybody.
Hello.
Let's start this adventure of sharing the screen. And okay.
Yeah, good. So everyone is familiar with the title and with our bios. So I guess we can skip to slide 3. And as we're the first one to speak, I'll let myself introduce Axel Springer to everyone. And some of you may know that Axel Springer is a publishing company. We own a couple of newspaper and magazine titles. We are also the largest digital publisher in Europe. Helena, can you see me?
I cannot see you, but
okay. So next one, please, and the next one, please. Yes. So altogether, we own over 250 brands. Not all of them are active in the media industry, but almost all of them are somewhat active in the digital market. And therefore, Axel Springer makes approximately 70% of its revenue from digital business. And this makes us believe that we're not only media company, but also digital or tech company. Next, please. So I guess now we can jump into the presentation. This is our agenda for the next 25 minutes or so. We will first introduce Upday and tell a bit about its activity. Then we will look at the article pipeline, so the path each article has to go through from the publisher to the end user of Upday. And with this background knowledge, we'll be able to proceed to our project, where we will look at the data, model search, and the model that we recently put into production. And then, of course, learnings and next steps.
Well, so let's start with what is actually Upday. And for that, I will leave a demo running in the background. So Upday is a news aggregator, so it's a news application that aggregates content from different publishers, and it displays the contents of these articles to the users in the shape that you see, so in the shape of cards. So a user would swipe through the cards, and whenever he wants to click on a card, he would land on the page of the publisher and read the full article. So there are two concepts in Upday. One is the concept of my news. So these are personalized news. What you're seeing now, it's a stream of, adapted to the user interest news. And there are other kinds of news called top news that are news curated by human editors that reflect the headlines of the day. So let's move on to the article pipeline. So as I mentioned, Upday displays news. So and actually, it displays news in Europe for over 36 different markets. So we have every day thousands of sources that we import. And let's look at the cycle of an article. The initial step is a publisher publishing an article. As you see here, let's say an article from the newspaper Welt. So for us, the first step would be to extract text, title, image, and other components from this article. And eventually, the article will arrive at a step that is the classifier. And this is what we will talk about today. The classifier step will assign a category to the article. It will say if the article is a news article or a culture article or a sports article. And finally, we will end up with an article in a shape that can be passed to the further services for recommendation, for instance. As you see here, this specific article got categorized into the literature category. Okay, so what was our project about? So we have already a classifier in place that is working very well. It's based on Elasticsearch and some rules on top. But it has the fact that it's a third-party application, so we have that dependency. And we also don't yet have a retraining pipeline in place for that classifier. So what we wanted is to have a new classifier that should work at least as well as the existing one. It should be based on a machine learning model. We want to own and understand this model for being transparent and for being able to iterate easy on this model. Also, we want to control to monitor its quality. And specifically now important for us, given that the application is growing in markets, we want to scale this to multiple language and reduce the costs.
So in the beginning of our project, we tried to identify some challenges that may cause our work more difficult. And about the one you can already think yourself, we had to integrate our classifier into the pretty complex and third-party owned system. So it was an interesting part of this project, I would say. We also identified some challenges regarding the data. Our training and evaluation data come from 2016. So as for the problem of news article classification, this data is pretty old. And we were not sure if the model trained on this data will generalize well on 2020 live data. We also had to work with the evaluation set that contained only around 10 samples per category. And this is not really enough to assess whether the model performs well or not. Unfortunately, we had to use it because the current system uses this data set for evaluation, and this was our only common point with the current system. So if we wanted to compare ourselves with it, we had to also evaluate on the same data. Next, please. So for the first iteration of this project, we decided to focus on 2 languages, English and Polish. And we did it for 2 different reasons. English is a pretty important language for Upday because there are many articles in English language going through the pipeline every day. And there are also many users using the app in the UK. And we also decided to choose Polish because it's a way more complex language, and we wanted to see if we will be able to train a model that will still perform well despite the difficulty of the language. As you can see, for both sets, we had 10 and 12,000 data points to train, and we had to predict over 80 categories. Next. So this is our training data. As you can see, we had category that we had to predict, and then title, text, URL, as well as the picture attached to the article. Next, please. And as I mentioned before, already in the beginning of the project, we realized that there were some challenges related to the data. And as we started data exploration and the first baseline model training, we identified even more challenges. So the first one is data imbalance. As you can see, some categories have way more training samples than the others. Next. Yeah, thank you. But more disturbing challenge is actually the inconsistency in labeling that we found. In this table, you can see 3 articles. All of them are about opera. The first 2 come from the training set, and the last one comes from evaluation set. And as you can see in the last column, they have different categories assigned. So majority of the training set, in this case of the opera article, was assigned to culture theater stage. And in evaluation set, it was common to classify those articles as music, classical music. Next. So we decided to dig a bit deeper, and for our baseline model, that was logistic regression, we generated feature importance charts that you can see here. As you can see, they are for those 2 labels I talked before. If you look at the left one, you will see that the word opera appears as a negative feature. So that means that if it appears in the title, it's gonna speak against classifying this particular article about as music, classical music. And if you look at the right-hand side, you're gonna see that for culture theater stage, it was one of the highest and most important features to classify the article. So yeah, next. So we decided to investigate it a bit further, and we picked 45 samples in the evaluation set that were misclassified by our baseline model. And we wanted to see how often it happens that our model was wrong and how many times the ground truth was wrong. And what we found was that the model was clearly wrong. And maybe here I should make the disclaimer that it was a team of data scientists assessing those articles, so we didn't get any training for how to label this data, so we may be a bit off, but we did our best. So 40% of the data of the samples, we actually made a mistake, so our model was clearly wrong. But in around 60%, either the ground truth was wrong or the content was ambiguous. And to give you a bit of the background for it, next. I prepared a table with 3 examples of those most common assessments. So in the first row, you can see the example of our model being wrong. We predicted music, rock music, whereas the article was about Chris Rock, who is an actor and comedian. So I guess unless our model has seen Parks and Recreations, it shouldn't have made this prediction. The next row is showing the example of ground truth being incorrect. Here, someone labeled this article as Culture Miscellaneous, but in fact, it's an article about advertising and marketing. And it also comes from the publisher that mostly sends us this kind of content. And the last one is pretty interesting because there were many articles in training and evaluation datasets that were very similar to this one. So we had an article that is clearly news, but it's also about politics. And for us, data scientists, and I guess also for content team members, it was impossible to tell which one is more correct. Oh, sorry, there were some questions, but I cannot really see them. Can someone read it out, or shall we move on? Okay, great, thank you. Yeah, so next.
So, okay, now we want to tell you about our workflow to finding a model that we want in production. So the first step for us was, of course, to deal with text preprocessing, given that the features that we had were title and text, also the URL. We started with the data cleaning, where we did some filters with regular expressions. We tried out different types of text embeddings, so bag of words, TF-IDF, and also BERT embeddings. The next step was considering which models were candidates for us. We consider models from the family of linear models, logistic regression, passive-aggressive, SGD, SVC, SVM, and multinomial base. And also we tried some models that are nonlinear, so the cat boost with a classification layer and BERT with a classification layer. For pipeline tuning, for the TF-IDF parameters, we worked with a grid search. For the linear models, we use Bayesian hyperparameter optimization to look for good parameters. Also, we did Bayesian optimization on the weights that we put on the features. So this was our way of selecting between, let's say, title features and text features and URL features as well. And finally, for the evaluation, our target score was the weighted F1 score. This was for two reasons. So one, because our data is imbalanced, and the other reason was that this is a score that we had in common with the existing evaluation on the, let's say, old classifier. Another tool we used during our experiments was MLflow. So for experiment tracking, this turned out to be very useful for us. We were able to track metrics, the models, the code, and to share these results among team members. So this was also part of our whole project. Now, regarding performances. So you see here, per model, the best score we achieved, ordered from bottom to top. So since the beginning, we got a good base score with logistic regression. We work on improving it, and it's still, for us, the best performing model. So together with a passive-aggressive classifier that, okay, it yields the same score. The difference is that it's much faster in training. Also, BERT, with not so much effort put into it, worked quite well from the beginning. So we fine-tuned it with our articles data. And now we have ongoing work to check if we can actually beat logistic regression with BERT. Yeah, in the middle, this blue line, you see the current classifier, the one that is based on Elasticsearch. And below that, we have a cat boost with bag of words embeddings. This is the like default classifier for text that we such the same with support machine. Yeah, cat boost, we tried it on the TF-IDF features that we actually used for the logistic regression. It did not perform well for us. Yeah, also knife base. doesn't look promising in our case. Okay, so from this last chart, so we took logistic regression as a first test for our classifier. And how did we integrate it? So now, okay, an article arrives to our pipeline. It goes through the classification step, and what we do is we tag the article with both methods, so with the old classifier and with the new classifier. And finally, as you can see in this box, the article gets a category old assigned and a category new according to each of the classifiers. So if you remember what Gosha was mentioning is that our training set is from 2016. So, and we deal with news. So it's, of course, data that outdates. So we really wanted to see how does it perform today, March or April 2020. That's why we pulled 1,000 articles, we gave them to content experts, and we let them check. And we had that in around half of the cases, both classifiers were right. In 1/4 of the cases, only our new classifier was right. In 50% of the cases, the other old classifier was right, and in the remaining cases, both were wrong. We took this chance to get new labels on this data, of course, and here you see other metrics on this new data. So the old classifier metrics and the new classifier metrics, you can see that both dropped compared to the evaluation metrics from the model pipeline. And actually, the F1 score, it dropped for both classifiers around 0.10. It shows how, model got outdated, though our model didn't drop as much. And it shows that our model can work well and actually can compete with this existing classifier.
All right, so let's move to the learnings. Next. So the first one is no-brainer. The quality of data and consistency of labeling is very crucial for the project. We definitely had to think and work a little more on the whole process, having in mind that, we cannot fully trust the data we test our model against. Next. It was also quite surprising to see that BERT, that is these days very popular and very useful for many NLP applications, didn't work or didn't outperform linear models out of the box. Of course, it doesn't mean it cannot. With a bit of tweaking it will probably get better than those linear models, but it was also nice to see that old good logistic regression can do a really good job on our data. And one thing that one needs to remember is that the performance can mean different things depending on the project. For us, because we knew that our model is supposed to be a part of a pipeline that needs to deliver stuff quickly, not only the prediction quality was important, but also whether the model is lightweight, because storing it on cloud costs money if it's heavy, if it can deliver the predictions as quickly as possible, because we need to meet the thresholds set by the third-party operator of the pipeline. And it was also important for us that the model can train and perform well even after it was trained on little data, because not for all languages we have a lot of data points available. Next. And actually, during preparing this presentation, we realized that we didn't get too much time to work on this project. We only worked part-time, 2 days per week, and we only had one person from each company working on it. So altogether, 2 people worked for about 30 days on this project. And it's nice to see that we managed to do a fair bit of experimentation, develop the app that will serve the model to the third party, and also run the evaluation of the live data. I think it's quite a lot. And of course, we were able to achieve it only because we prioritized. So I'm sure that some of you thought during this presentation that, oh, maybe this model would be better. Or if you invested enough time in experimenting with some other model, it would have surprised you how well it works. Unfortunately, we didn't have all the time and all the resources to look into all possible solutions. So we had to prioritize. And I think we did a pretty good job here. Next. And speaking of experiments, like Helena mentioned, we used MLflow, and it was definitely very useful. We were able to compare the model we trained yesterday with the model that we trained weeks ago, and we didn't really remember what was the state of repository back then. So it was really helpful, and all of us were new to MLflow, so it took us a little bit of time to set it up and figure out how to design the experiments. But it was a very helpful learning for us because I could definitely tell that our further or later experiments were designed in a much better way than the first ones. And I think each of us will use it in the future. And last but not least, it was very, very helpful to closely cooperate with our stakeholder, that was the content quality expert. We were meeting regularly to present our progress, align for the next steps, and hear the feedback of the the main beneficiary of the product we were building. And it was really great that they managed to assess live data, like 1,000 articles for us, so that we actually know how well our model performs. Next. All right, next steps. So we're getting to the end of this iteration, but we still want to continue on working on this project. And right now we're looking into continuous integration, and we're designing the strategies for quality monitoring and retraining the model. And in the future, we would like to, of course, also expand to further languages, and maybe one day also look into replacing some further elements of the pipeline. Questions?
Okay, I think I stopped sharing this, right?
Let me. Can you hear me? Thank you very much for your very nice talk, Helena and Kosia. There are a lot of questions, over a couple of dozen. Many of the questions you actually answered already during the second part of your talk, so I don't need to pose them here. I think most people were very surprised to learn that logistic regression works better than BERT. Do you have an explanation for that? For like 2 or 3 questions in that direction.
Yeah, we believe that it's rather the matter of working a bit longer for on this model, because we took an out-of-the-box solution, and they rarely are the ideal setup for your project. So perhaps in the case of the English language, it's not such a high priority, because we're already doing well and better than the existing classifier. But for the Polish language, where, well, we didn't mention this part of the project because we wanted everyone to be able to read the examples we prepared. But because this language is a bit more complex, logistic regression didn't do so well on it. And well, I can tell you that it was about I think 0.76 F1 score. So we would like to do better there, and our first attempts with the Polish pre-trained weights of BERT were way more promising than for English language. Yeah, so maybe it depends on the language.
Thank you. There were a couple of other questions that was asking about how you determine the weights or the ranking of the words within logistic regression.
Okay. So for whoever uses logistic regression, I mean, the nice thing about logistic regression is that it's quite transparent about it, so that you can look at the weight, I mean, like at the matrix itself that you multiply with your features. And this is actually what we were showing us. Let's say we took the column that was responsible, let's say, for the category classical music, and are the weights that you show. I mean, you just add the labels of your features, and then you get this nice visualization.
Okay, thank you. A few short questions. What vectorizers did you use?
Okay,
I mean, I guess word tokenizers they meant.
I see. We tokenized by separating Gaussian, like the spaces, and we didn't split by something else than spaces. I mean, we did remove some special characters, and we did replace numbers by, let's say, zeros, but nothing more fancy.
I mean, we did quite some testing there too. We tried the very simple text cleaning, but also removing stop words and these kind of things. And then we tokenized it with TF-IDF.
Okay. That was actually also one.
So it was a combination, a combination of these two.
Yeah.
And our finding was that actually doing like overdoing the text cleaning doesn't help in any way, because the TF-IDF is smart enough to deal with most of the things we tried to hard code in the text cleaning part.
Yeah, maybe especially exactly removing stop words for us didn't pay off. I mean, using TF-IDF, either we kept the performance or it was even a bit lower when we did remove stop words.
There was a question about, did you try to use the first generation of word embedding, say fasttext or word2vec?
We did not.
Then, from the many other questions, did you try to resample to balance your data set?
Yes, we did try. In the beginning, we tried, and it also, for us, did not work well on our evaluation set. I mean, balancing did not improve our metric. Yes.
Okay, let me pick a last question. Yeah, it's a very elementary question. How did you plot the feature importance in one of your first slides?
I see. Isn't it related to the first question, like how we got this?
Yeah.
Okay. Yes, I mean, you have the coefficients matrix from the linear regression model, and I think we just put it in a data frame, then transpose it so that you have nicely, I mean, you can, and you get feature names also from the model directly?
We can share the snippet that we use, because it's pretty simple. You take the names of the features from your word embedder, so in our case TF-IDF, and then you just make a huge matrix with all the coefficients that are, well, in logistic regression you have them all stacked in the same order. So yeah, it's a very simple operation in Jupyter Notebook.
Okay, yeah, it would be great if you could share that with the community. A lot of people will be very happy, I guess. Many more questions. I see while you were answering, more questions pop up. But Trent, I think we should move on to the next speaker. Could you do the introduction, please?
My pleasure. Sure. So let's go on. So the next speaker is Tanuj Jain from Axel Springer AI. And he's working as a senior ML engineer at Axel Springer since December of 2019. He was previously part of the data science team at Idealo, and his current interests are around deep learning research for speech and image processing. He got his MSc in electrical engineering, yay, NEE, from Paderborn University in 2015, and he's been working in the field of data science ever since. And he's interested in leveraging the power of ML to empower businesses and measure the impact created. So please take it away, Tanuj.
Thanks, Trent. You just saved me one slide worth of trouble for the comprehensive intro. So just let me begin by sharing my screen. All right. I guess you see this now. All right. So I'm going to talk about a Python package that my team and I built called imagededup, and it's going to help you to find duplicates in your image collection. Now, Trent talked very extensively about who I am, so I'm going to skip it, which brings me to the fact that my team and I really, really like open source, not just consuming it, but also contributing to it. And here you see a screenshot of a bunch of our open source efforts, imagededup being one of them. Our latest efforts are centered around speech and natural language processing use cases. So the biggest thing for us at this point is the first repo called forward tachotron here. And it's a text-to-speech repository. I'm going to quickly play a snippet just to show that this thing works.
Hello, I am a generated voice and welcome you to the Berlin Machine Learning Meetup.
Cool. So just have a go at it, see it works for you.
Hello, I am a
Okay. Now let's skip to the agenda. First of all, I'm going to be talking about the motivation part of it, as to why we needed to handle this use case and make another Python package out of it. Then I'm going to be talking about a bunch of components that I think or we thought were important for the system, followed by a quick demo and a summary. So now to motivate the examples, I have two examples from the real world for you guys. The first example is from the domain of e-commerce, and the second one is from the domain of hotel comparison portals. I pre-clicked the link so that I don't suffer from the curse of demo. Where am I? Yeah, so the first link that you are going to see is actually a gallery from one of the e-commerce websites. And what you see here is basically an iPhone, and this is the first image. To your left, you see a bunch of images there. So I click the second image and the third image, and you basically see it's the same iPhone, but with different colors. Now, if I scroll through the entire gallery, I see like, whoa, there are like, I don't know, 18 different colors available. And that's like a happy scenario for me. But if you look a little deeper, you're going to arrive in the middle of gallery with this image. And which is this image? This is a black image. Now, if you're like me, you're probably going to be feeling like you're colorblind because, well, when I checked my first image, it was also a black image. And I was wondering whether I'm colorblind or not because it's the same image. And you see this pattern repeated over and over in the gallery. So you have the potential to get misled into believing there are more options when you actually have a few. The second example that I want to draw your attention to is from a hotel comparison website. And what you do is typically you're looking for a hotel, you put in your filters, and then maybe you look at 10 hotels as your prospective places of dwelling. And what you do then is you go through the galleries of the image of the hotel to see if you like the hotel enough to book it. And there you see images and galleries like these. So these are two separate images, but in the same gallery. And I don't know about you, but if I have 10 hotels to check out and like 100 images for each hotel to see, I don't want to be subjected to duplicates. So there's not a lot of strength to looking at one image over and over. Of course, if the image belongs to the person you are romantically interested in, that's a different question, but generally not. So you're going to be annoyed like this little lady on the screen if you have to watch the same image over and over and over. Now, moving on, it's not just that we care about what gets displayed on our galleries for business. Me as a machine learner is also interested in making sure that my train and test sets do not have the same samples, because that would constitute a leakage. And in fact, you see a link to an interesting paper that talked about this same problem in a very famous data set, actually Cypher data set. So all Cypher 10, Cypher 100, and so on. So as a machine learner, this makes a lot of sense for me. Now, at the time when the package was developed, my team and I were employed at Idealo, like Trent mentioned. And when you're working with a company where you have a lot of tech teams, a lot of whom have to deal with image use cases, you have specific challenges. Some of which are, well, you have every team working with a different tech stack. So some might be interested in Python, while some might be interested in PHP and so on. Then you have communication challenges. So maybe team A already has a solution for deduplication at their end, but team B, who needs a solution, has never talked to team A and doesn't know about the existence of the solution. So team A basically starts developing their own solution, which leads to redundant work. Thirdly, you might have a different definition of duplicate depending on use case, and I will go into a bit of a detail later on about this point. And then, of course, you have varying areas of expertise. So in the last couple of years, some of the methods, especially those that are deep learning based, can be leveraged to do this, to tackle this problem. And if as a developer who's not into deep learning or a lot of these advanced methods, it would be a lot of learning curve for you to actually make use of these techniques. So we took all of these considerations and we realized we needed a standard solution for this. Now, when we were still thinking about building a solution, we had a bunch of epiphanies. We realized that we're not the only e-commerce or hotel comparison people. We actually are not the only ones, and there are a lot of other companies and other businesses that could leverage such a solution. And not just businesses, like an average person, maybe an Instagram addict who takes like 1,000 photos every day, may not want to keep all of them. So even at an individual level, it could provide some value. And combining the fact that we believe a lot in community efforts, we decided to model this as an open source solution. Now, this was not our first foray into tackling image deduplication problem, as I mentioned, because as a machine learning, like I said, machine learner, we tackled a lot of image-based use cases and had already gone through the rigmarole of developing such a system and using it for our machine learning models. So we narrowed this down with our experience and with the other points that I mentioned earlier, that we could have basic set of technical and user requirements, which are, for technical, as image deduplication system, you need something to generate features. Then you need, using those features, a search mechanism, and then something to evaluate how good the deduplication is. I would go into a lot of detail about this in the next slides. Now, for the user requirements, the solution needs to be usable right out of the box. You do not need to know a lot about algorithms in order to use them. And you should be easily able to use this in a basic programming language, even if you maybe spend 3 hours learning the programming language. We also wanted to keep the API design very simple, so none of those function calls with 30 parameters in there. And we found that there was nothing already out there which satisfied all these requirements. So we said, okay, we need to build a Python package ourselves. And why Python? Well, because we are Python people. Now, this concludes the motivation part of it. So I hope you understand why we actually chose to tackle this problem, for which there are already some solutions out there. Now, let's go into the details of 3 basic components of an image deduplication system, or what we figured out were the basic systems. So these are feature generator. Second is you need some search and comparison mechanism that uses these features to say something is a duplicate or not. And then you need to evaluate how good a particular deduplication algorithm is for your data set. Now, let's talk about the first component. The first component is, well, it's pretty self-explanatory. You have something that generates a representation of your image. So on the left, you see image of our dear old Mona Lisa. I think she's been used heavily across the image processing community. You apply some feature generator on top of your dear Mona Lisa, and you get some features out of it. Now with imagededup, you have a possibility of using 2 broad set of feature generation algorithms. The first set of algorithms are hashing algorithms, which you see represented to your right. And the output is 64-bit hash, here represented as 16-character hexadecimal string. Or you could have the output features as a vector, which basically is a vector of floats. Now, with imagededup, you have 4 different kinds of hashing algorithms possible: perceptual hash, average hash, wavelet hash, and difference hash. And there's only exactly one vector algorithm here, which makes use of convolution neural network. Now, because of shortage of time, I cannot go into the details of every single hashing algorithm, so I'll just choose the best that I like. So let's talk about difference hashing. Now, the basic concept of difference hashing is the gradients of similar images should be similar. On the left, you see 2 images of Mona Lisa, which are actually different images of Mona Lisa. And to your right, you see the respective gradients. So here you see that both of these gradient images actually have some similarities and some differences too. So if you look at like the edge of the face or the hands, you see there's actually quite a lot of similar content there. Now, let's see the steps of image hashing. Different hashing. The first step requires you to resize the image. So you take the original image and resize this to, in this case, a 9x8 image. 9x8 because we want to generate a 64-bit hash. This is followed by conversion of this RGB image to a grayscale image. So Mona Lisa lost all the color that it had. Then this is the step that actually generates the hash. So just leave out the first column of the image. And for all the other content of the image, go to each pixel and basically apply a rule which says, look at the pixel to your left and see if it is dimmer. So if the pixel to the left of the current pixel is dimmer, you put a true here. If the pixel to the left of the current pixel is brighter, then you put a false here. And you end up with the 8x8 Boolean matrix. Now, the next step is pretty trivial. You just take this 8x8 Boolean representation and make a 64-bit hash out of it, which you can represent as a 16-character hexadecimal string. So this concludes the discussion on the basic difference hash. Now let's just quickly talk about convolution neural network, which basically generates image embeddings. Now, what you see on your screen is a particular architecture of convolution neural network architecture. On the left, you see an image, and which gets propagated throughout the entire architecture. And here you see a final output layer with the number 1000 on top of it. Now, what we did was we took a pre-trained convolution neural network, actually, which is called MobileNet, and this is not MobileNet, but it serves the purpose of the presentation. So you took the MobileNet that was pre-trained on this data set called ImageNet, very famous data set, and has 1000 classes, which is the reason that you see 1000 to your extreme right. Now, if you train a network well, you might know that different parts of the network respond differently to different patterns in the image. So maybe this particular part of the neural network actually responds best to these small patterns that might detect in the input cat image, while a later part of the network might respond to more fuller patterns like the ones that you see here. So in principle, if a network has been trained well, it has been able to gauge the capacity to respond differently to different patterns in the image. So the hypothesis is, well, if you pass a different image, then a particular layer will react differently and uniquely to that image. And that is the main reason we can use convolution neural networks to capture the uniqueness of an image. And how do you do that? Well, instead of propagating the image to the end, which is the label output, you make a cut somewhere, let's say here. And you take the output of the last cut layer, and you generate some representations, which you can call embeddings or encodings, whatever you like. And because our assumption is that we are unique enough with our representations, we should be able to say whether some image is similar or different. Now, let us move on to the second component. So on the left, you see your image corpus right now with 4 images. You apply some feature extractor. And if you use hashing, you generate some 64-bit hashes for each image, which you can see on the right. Or if you use the convolution neural network, you generate some float arrays for each image. Now, once you have these hashes or these vectors, the story doesn't end here. You have to be able to compare different hashes or different vectors in order to say whether they are duplicates or not. So for hashing, you can use a simple distance metric called Hamming distance. And basically, as you see on your screen, you represent each image by hash. Let's say we use difference hash. You see a very simplified binary numbers here for the demonstration. And you basically see how many positions these numbers differ at, which is marked in the red columns. And this gives you the Hamming distance. So if these are the hashes for these two images, the Hamming distance between the images is 2. Now, what do you do next? Based on the Hamming distance that you get, you define basically a threshold which says, okay, if the Hamming distance between the two images is greater than my threshold, then the images are too different and they're not duplicates. Whereas if the Hamming distance between these two images is small enough, then you say, well, it's a duplicate. Now, as you can imagine, this is going to take a lot of comparisons. So for your 4 images in the data set, for each image, you have to make at least 3 comparisons and find the Hamming distance between each of the pair of images. So this actually, as you already might have guessed, is pretty inefficient, especially more inefficient if you work with pure Python. So what did we do here? We actually used Python for implementing brute force, which made this particular search feature orders of magnitude faster. Now, the Python implementation actually came as a pull request. So here again goes our case for using open source. Secondly, we also tried to use this specialized data structure called BK tree. And what it does is it creates indexes of all the hashes and basically reduces the search space. This means you have to do fewer comparisons compared to brute force. And of course, since each of these Hamming distance calculations is basically unique and can be done in parallel, we use multiprocessing to parallelize this. Now, let's just quickly see how convolution neural networks basically are used to generate similarity. So it's the same regime, same images, but this time, since you use convolution neural networks, you get image encodings or embeddings. And what you do is simply you pass this to a cosine function, and you spew out some cosine similarity distance. Not distance, cosine similarity here. And let's say this cosine similarity is 0.8 here. Then you put a rule there using a threshold, which basically says, well, is this cosine similarity calculated here more than my similarity threshold? If yes, it's a duplicate. Otherwise, the images are too different and it's not a duplicate. Now, one thing to note here is that the semantics of the metrics are different for hashing and for CNNs, because with hashing, we're talking about Hamming distance. And with convolution neural networks, we're talking about similarity metric. So just keep that in mind when you give ImageDedup a go. Now, similar to hashing, we had some optimizations to improve the search time here as well. So of course, we use matrix multiplication, and to save some memory footprint, we actually calculated the cosine similarity in chunks. And similar to the hashing regime, we used multiprocessing to parallelize these computations. This brings me to my third component here, which is evaluation. Now, if you remember at the beginning of the talk, I talked about the concept of exact and near duplicates. Here you see 3 groups of images. On the top left, you see 2 Mona Lisa pictures, which are exactly the same pixel by pixel. Now, a lot of people, when they say duplicate, might mean this. However, on the bottom, you see Mona Lisa's picture and a rotated version of Mona Lisa. Now, for many use cases, maybe this is a duplicate. Maybe for some use cases, it isn't. And on the top right, well, you actually see, again, 2 Mona Lisas, but these are actually 2 different paintings. So it's easy to say that, okay, both are actually Mona Lisa, but it's also very easy to say that they're obviously not the same painting. So depending on your use case, you might have a varying definition of what a duplicate is. This brings you to a bunch of conundrums here, which is basically what is a duplicate for you? And there are 5 different deduplication methods that are available with ImageDedup. What do you use? And for each of these deduplication methods, there are different threshold values. So what do you do? How do you figure out the best combination for yourself? Now, to answer this precise question, we actually built an evaluation framework there. And how do you use this evaluation framework? Well, you first take a subset of your target image dataset, and you take the manual effort of annotating which image is a duplicate of which image in your subset, right? Then what you do is you pick up an algorithm of your choice from ImageDedup and a corresponding threshold, and you pass this entire subset of image data to the algorithms, and this will actually generate an output. Now, basically, with step 2, you have an output generated by your algorithm, which says this is what it thought was a duplicate. And in the first step, you already know what exactly is the ground truth and what should be called a duplicate of which image. Now, if you have these 2 maps or these 2 outputs, you can pass this to our evaluation API, and this is going to give you your familiar metrics like precision, recall, mean average precision, and so on. And you can apply step 2 and 3 over and over, and basically reach a part where you can select a particular method along with the best threshold. And to make your life a little easier, we already have done some benchmarking, and you see already the link in the presentation. All right, this concludes my discussion. Now I can show you some demonstration, and I hope it's useful. If I can find my mouse pointer, it'll be great. Otherwise, okay. Okay. So the data set that I'm going to try and deduplicate here is actually comprising of the 4 images that you saw in the presentation, and there are a few more images as well. So how do you use this package? So installing the package is very straightforward. Just pip install ImageDedup. And if you are looking for, if you have access to GPUs and you want to use convolution neural networks, you just have to install on top of ImageDedup a TensorFlow version that supports GPU. Nice. Okay, so let's start. Let's see how to apply difference hashing to our use case. So the API is pretty simple. So you say from ImageDedup.methods import dhash, which you execute. And next you initiate the instantiate the object. And then you use this simple function called encode images, where you provide the path of the image directory. And this will give you encodings for all the images in your data set. And this is what the encodings variable looks like. So this basically is a dictionary where the keys of the dictionary are the file names of each of the files in your image directory. And the value of each corresponding to each key is the correspondingly generated difference hash. And just to see how many images we have 11 images in the data set. Now, once you have generated these encodings, you can use another simple function called find duplicates and pass it the encoding maps that you just generated. And voila, you have your duplicates here. If you observe the output of the variable duplicates, again, it's a dictionary, and the key of the dictionary correspond to the file names that you have in your data set. And the output, the value of corresponding to each of the key is a list. What does this list contain? This list contains basically all the images that were found to be duplicate for the key. And as you can see, for the first image called Gioconda, that's actually the Mona Lisa image that I had showed you earlier, which is the Mona Lisa right now on your top left. For this, you find duplicate as the original Mona Lisa. There's also another exact copy of original Mona Lisa called original copy. So here you can exactly need to see what is a duplicate of what. And of course, there are some particular files for which you don't find any duplicates, and for them, the list is actually empty. Now, what you can also do is you can plot duplicates that you just found. So you can provide the image directory using, where's my mouse? So you provide the image directory, the duplicate map that you just found, which is the last variable, and you provide file name, which is original, let's say, and you plot this. So what you see here is on the top, the image for which you were trying to find the duplicates, and on the bottom rows, you find the exact duplicates that you found there. So you found this is actually the exact duplicate. This is like a near duplicate, so our Gioconda image. Now, let's see what you do if you also want to find out the Hamming distances between each pair of images. So here, this is something you can achieve by using the simple scores attribute, which you can set to true. And if you look at the output here, again, it's a dictionary with the keys as the file names. But this time, along with the duplicate file names, you also find a Hamming distance. In this case, the Hamming distance between Gioconda and original.jpg is 10. Now, you can also use CNN. Again, the API is pretty simple. You say just from imagededup.methods, import CNN, which you do, and you instantiate the object, followed by a use of, again, the same function called find duplicates. And here, instead of generating encodings first, you can actually directly pass the image directory. This is exactly, this is like uniform across whatever method you use. And using this find duplicates method, you again generate a duplicates dictionary, which again is exactly has the same format. But here you see that for Gioconda, you did not find anything. While for original, you still find other, just a second, yeah. You just find other, basically, images. Now, similar to hashing, you can also find duplicates along with the cosine similarities, and which is accomplished again by the very same variable called scores, which is set to true. If you inspect the output, apart from the name of the image, you also get a cosine similarity between the image and its duplicate. Again, plotting the same thing. Well, this time you see you just found for original image, one image with a cosine similarity of 1. Now, of course, you may have a custom definition of a duplicate, which is why you may be interested in varying the threshold. Now, for CNNs, this threshold parameter is called min similarity threshold, which by default is set to a value of 0.9. So here I became a little more liberal and set it to a low value of 0.6. Let's see what this gets us. Now, what you see here is, well, a lot of output. So for your Gioconda, .jpg, for which you didn't find any duplicates when you ran CNN last time, now you actually find 1, 2, 3, 4, 5 duplicates here. This comprises of the original Mona Lisa picture with a high duplicate score of similarity score of 0.82, plus a bunch of other Mona Lisa picture, a bunch of other pictures, but they have a considerably lower similarity score. Now let's just plot this and see what we get. Now, since we went pretty liberal with our threshold, for this original image, well, you find the Gioconda image with a high similarity score. You find the original Mona Lisa, again, which is like just a copy of our query image with a high similarity score. And you also have a bunch of other images, but the similarity scores are lower comparatively. And just like you could vary min similarity threshold with CNN, you could also vary the max Hamming distance threshold with your hashing methods. This concludes the demo time. And now I will conclude by summarizing. So we have access to 5 deduplication methods, which are available out of the box to use. You don't have to be an expert to be able to use this package. The API design is as simple as it can get. The installation is also straightforward. You have the ability to customize your definition of duplicate and evaluate this using evaluation framework. And you can learn more about the project at the repository and read the documentation. So maybe do give this a go, and if you face any issues, well, raise the issue at the GitHub repo, and maybe we can collaborate. All right, that's my time.
Thank you very much for your talk, Tavush. We've got a few questions. One question is, why did you use MobileNet as opposed to, say, VGG 1619 or Inception version 3 or something like that?
Great question. Prior to building this package, we had experience of doing a lot of image-based use cases. And what we always figured out was that ImageNet actually served our needs really well. Someone's mic is on. Yo. Sorry. Yeah, sorry. Okay, so to continue the question, the answer to the question, in our previous experience, we had figured out that MobileNet was actually a very good architecture. Add to the fact that it's actually pretty lightweight as well. So you get fewer flops, you get fewer parameters, and even actually a small memory footprint. So compared to other big networks like VG16, ResNet 50, and so on, it's a lightweight architecture which actually really works well. So that's the question. That's the
okay. Did you do fine-tuning on that pre-trained model?
No, we actually decided to do the easiest thing possible. And the reason for that is because when you talk about fine-tuning, you might have to consider your custom definition of data set. So it might vary from data set to data set. And we had done enough experimentation to know that MobileNet has good enough capability to capture uniqueness of each image. So
here's a very nice question. So you use MobileNet. MobileNet is pre-trained on ImageNet. Now the question is, can you also determine the duplicate images if an object is not present in the ImageNet dataset?
Yes, it's a good question. So it basically builds into the generalizability of MobileNet as a whole. So the reason that a lot of people tend to go with datasets like ImageNet is not just because it's public domain, but also because it has like 1,000 output classes. Now, if you have 1,000 output classes and enough data, you can say that the network, you can hope that a network has seen enough number of images, enough number of patterns to be able to discern between different images and generate faithful encodings. Yep.
Another question is, did you use other types of networks, Siamese or GAN networks?
Good question. We had started an endeavor in this direction. The precise endeavor was trying to work with the autoencoder. But the thing is, at that point, we realized that since it's a Python package product, actually geared a lot more to an average user rather than a machine learning user, the strategy we will adopt is we'll just put out the basic thing, and then we'll let the community ask for more. So actually, no one in the community has really asked for like a machine learning solution there. And I can think of why that the reason is because a lot of people actually just want to use something out of the box. This is also the feeling that we had when we were tackling our image deduplication problems before the package was made. So not a lot of people want to spend time like training networks just to deduplicate. But if you feel there's a quick need for this, if you're passionate about it, maybe raise an issue on GitHub, and let's get into conversation about it.
All right, thank you. A few other questions. We're concerned with what happens if you tilt or rotate an image, or if you flip it or have a mirror image of it. Is it a duplicate or not?
So basically, the first part of the answer is it depends really on your definition of what a duplicate is, right? And let's say for you, a horizontal flip of an image constitutes a duplicate. Now, unless the image is symmetric, hashing is a bad idea. So if you're trying to use any of the hash methods and you hope to determine like a horizontally flipped image, or a vertically flipped image, then you're going to find very different encodings because the gradient changes if you talk about hash for sure. However, you would have a much better luck working with convolution neural networks because they are robust to these kind of transformations. And if you have some experience of training image-based neural networks, you would recognize the fact that you often augment your data set. And one of the augmentation steps is actually flipping that you can undertake. So you have to be careful about what your definition of duplicate is and actually try to pick out an algorithm that suits you. However, to add to that question, we had the same doubt and we wanted to be sure of it. So there are extensive benchmarks that you will find on the documentation of the package where we have worked with these transformations and tried to determine what works best for each.
Final question is concerned. A couple of questions were actually concerned with the threshold. So the question is, how do you decide the threshold?
So we conducted some experiments and wanted to come up with some sensible defaults. And basically, the thresholds that you got here are more or less achieved through experimentation and trying to figure out what other people are doing. So, I mean, one thing that I should really point out here is, as some of you might already know, in terms of algorithms, there's hardly anything unique about the package. So hashing algorithms have been in practice since forever. Convolution neural network embeddings have been used for at least 4 or 5 years. So we had access to a good amount of literature to see what some sensible defaults would be.
Okay, thank you very much. And with that, I guess, Trent, could you... Oh, yeah, go ahead.
Yes. So again, 2 parts to the answer. The first part is if you are looking for, again, like an out-of-box functionality, then imagededup is not a very good choice at this point because you can run into memory issues or speed issues. But you can be a little smart about this and divide up your big data set into smaller pieces, and you can run this algorithm on each of the smaller pieces. So we would, in future, look at making this more available right out of the box and make it more scalable.
So yeah, some people could not hear the question. The question was about scalability of this library when you have hundreds of thousands of images. And so amazing talk, Tanush. Thank you very much.
Thank you.
So now off to Trent for the next talk.
Sounds good. Hi again. Let's see here. I'll go on video again too. So yes, we have one final speaker, and it is Carl. Oh, let's see here. I'll just go. So the speaker is Carl Przylski, and he's CTO and founder of Codete. He obtained a PhD in CS from the Institute of Fundamental Technology Research, the Polish Academy of Sciences, and he is also a research assistant at the Jagiellonian University in Krakow. And his role at Codete is focused on leading and mentoring teams. The company has built a research lab that's working on ML methods and big data solutions with specialization in pattern recognition and HTTP implementation. So please take it away, Carl.
Hi, thank you for the introduction. I hope you hear me well. Yeah, so I'm specializing in pattern recognition. I will show you some examples today. So I will talk about explainable AI. That's something that you, I guess, know already. Some part of the presentation will be, 1 second, why isn't it going? There we go. Will be focused on the skin cancer and how to get FDA approval. So how to explain your models to be approved to be used by the doctors at the end. One of our articles that you can download at Check, it's a multispectral skin pattern analysis. We used the methods in this case as well for some of the patterns. Is quite recent. I mean, in 2017 it was published. So obviously we will get the slides. We also have the link. So yes, I'm currently running my own company from 2010. Consultancy also in machine learning and data science. I'm also a data scientist. I'm doing machine learning for about since 2007, so 30 years already. And just a few words about the company that I'm building different kind of customers. Now currently we are working with Stanford University on some of the corona cases, especially the RNA analysis. Before that, we worked on some asthma detection algorithms. It's pure. Oh, it's poor, the quality. I hope. 1 second. Let me just double check. And what about now? Can you hear me better? Okay, cool. Sorry for that. Okay, cool. So yeah, the RNA corona analysis that we do together with the Stanford University, the asthma detection app that we also do with Stanford University, but we also do different kind of projects for different kind of companies from automotive like BMW, Daimler, or yeah, coming back to Berlin, for example, Home24, WebTrack. These two are actually from Fiber, is also from Berlin. Raisin is from Berlin. So we have several customers that we work with in Berlin. We have also an office in Berlin, and yeah, more or less. That's about the company. So before I go into the explainable AI part, I would like to talk about how I started the research on the melanoma. Now we have obviously the hype. So every time everyone is talking about the AI is the new UI, AI is the new electricity. Everyone wants to use AI. I know today because of Corona, probably it will be a bit limited. But since 1 or 2 years, on artificial intelligence or machine learning specifically. And when I started my research on skin cancer, it was very hard to. It was in 2007, 2008. It was well. It was really hard to get any kind of images to do the research. Even at my university, we have a hospital actually. Just a department of doctors, of medical doctors, that are actually doing the analysis of melanomas or of skin cancer cases. Even these guys didn't gave me any images because of many cases. Obviously, now we have also GDPR, which makes it actually the case even more difficult. But now you can use the ISAC archive to download actually text. So imagine when I started my research, I got from my colleague from the institute, from the department, about 56 images. So you can imagine you cannot do really any kind of research having just 56 images of skin cancer cases. So I spent a couple of months to get a data set, and finally I get a data set from 5,000 images. So it's still not the size. It's still not the size that you can actually download now from the ISIC repo, but it was a quite huge data set for that time that when I started. Now everyone is doing it. Everyone wants to do any kind of deep learning, machine learning, data science projects, or yeah, and that's something that is totally different comparing to what is actually what we have now. I mean, what we had before. When I approached the customers in 2010, when I started the company, it was very hard to convince the customers to actually do any kind of machine learning because they didn't have any reason actually. And the reason was because I had arguments, but they didn't want to do any kind of machine learning project. Now it's totally different, which is good. But on the other hand, it makes it a bit more problematic, because take a look on this research from 2019, from last year, 40% of AI startups, actually Europe doesn't actually use AI. So why they tell they use AI? Well, because they get more money, from 15 up to 50% more money, because they say they actually do AI. So that's something cool. I mean, cool because well, if you would be asked to, if you would know that you will get from 15 to 50% of more money if you tell the investor that actually use AI or would like to introduce AI, then probably you would do it. The thing is that it makes it a bit more complex, especially in any kind of regulated company. And many projects, AI project fails for many reasons. One of it that actually they use it because and they don't actually need it, or they use it because of the hype, because of many reasons, actually. And Gartner saying that actually 85% of AI projects really fails. Just to give you some cases. So obviously, explainable AI can be used in not only in hospitality. Actually, that's a typo. We can use it in different kind of areas. The same actually like in typical artificial intelligence. But the most typical industries where actually explainable AI is used is the medical diagnosis and financial analytics. Why? Because these two industries are regulated. It means they have someone above, from the government, for example, that is telling them what they can use or what they cannot use because of some reasons they cannot use, because it's not proven that some methods works, for example. So let me give you some examples. I'm not sure if you heard about tweetbot. That's an example for 2016. It's a solution from Microsoft. They used this tweetbot, and after 24 hours, it became a from a teenager profile, it became a different kind of racist profile, actually. Or another one, it's a quite new one from 2019. I guess you heard about it. Amazon Alexa, it's telling that actually you should suicide yourself, right, for a greater good. Another case. I'm not sure if you bought already the T-shirt with this image to not be recognized. Not to be recognized in as a person by the convolution, actually by neural networks. So I have a separate presentation on just advertiser attacks. It means fooling actually neural networks. So why I'm showing you this kind of cases, like the Tesla one here. So the Tesla, 2017, the Tesla car crashed into a truck because it was recognized as the background. So that's something that is also, it shouldn't happen, right? And explainable AI is used actually is one of the methods to, first of all, kind of debug what is actually the method doing, but also to explain also how it works for someone who is non-technical. So there are many reasons why we should use explainable AI to figure out what actually went wrong. I hope it will not go wrong, right, in many cases. But sometimes it is, and we cannot avoid it because it's getting 100% of accuracy. It's really, really hard. So why use explainable AI again? Well, there are different kind of goals for explainable AI. So first of all, understandability. It's also known as intelligibility. The model should be understandable by humans. So it means that the model should work with without the explanation of the internal structure of the model or the architecture. So we are able to explain it. Also, we don't know how actually the data process. So that's one of the explanations of explainable AI. So I mean, I mentioned just 4, but actually, if you go into and take a look on some articles or books, actually there are not so many books on explainable AI yet. But if you go into some articles, you might find more than just 4 terms that are related to explainable AI. So comprehensibility actually it's something. It's about. It means that a method is able to represent its learned knowledge in a human understandable fashion, right? So the way how it works should be done in the same way like a human expert would do it. So that's what the comprehensibility is about. So interpretability, obviously, it's understandable it's defined to be as the ability to explain or to provide the meaning in understandable terms to a human. And transparency, well, there are 3 levels. I mean, depends on the article, but most of the articles mention about 3 different transparency level, and it's about, well, it's about how can we simulate it, or how, if we are able to explain just a part of it, like a layer, for example, or part of the whole model, or can we simulate it the whole process? What's happening with the data? I will come back. I see there's a question regarding finance. I will come back to it in a minute. So there are several goals of explainable AI. I didn't mention also all goals, just to mention a few. So the confidence and trustworthiness. So everyone wants to have a model that actually is robust, right? So we would like to have a model that we are sure that we are confident of the prediction that is giving, right? So, and actually we would like to trust it as well, right? So the causality is about the variables features that we provide, so understand it as well. Transferability, that's something tricky, because if let's imagine that you are developing developing some software. I mean, not machine learning. I mean, typical, like doing something in Java for a web application, for example. Then some of the code can be actually reused in some other application or some other part of the company, a different project. And transferability in explainable AI is actually to reuse the knowledge that we have learned in building this model, to use it in a new one, not just by copying paste the layers or part of the neural network, but actually having the knowledge to understand what's actually happening. So that's about transferability. Informativeness, obviously, it's needed. We are able to actually have we are able to relate the user decision to the solution given by the model. So that's what the informativeness is about. So we avoid failing in misconception pitfalls, for example. So fairness is about, well, the model should be fair and ethical, right? So the case with TIE, for example, right? So that's not what we expect to have in our model. And explainable AI should give us the possibility, the implementation of some explainable AI methods should give us the confidence about the fairness, so be sure that actually the method is working in an ethical way. And it's a bit more, it's a bit more tricky now, because it's highly related to the data that we're using for the training. But I will come back to it in a minute. So accessibility as well. So allow the non-technical persons to actually deal with the model. Interactivity as well. We would like to interact with the model and tweak the model as well. That's something that we also consider be one of the goals of explainable AI. And obviously privacy awareness. So it's we should actually use the data and the model that is actually used. The model, I mean, the weights that we train, for example, nothing actually will leak from the data that we used as for the training. So there are also levels of transparency. I cannot go deep into this topic because I'm limited of time. Especially I've just a few demos in a minute. But I can send you some materials later, some links to share if you want to go deeper. So where we would like. Why should use actually explainable AI? So who actually should use it? So first of all, the domain experts. Let's imagine you have a doctor, a medical doctor that is diagnosing giving it a diagnosis in skin cancer. So using actually a tool that that he is using for let's say supporting this doctor in giving the diagnosis. It's also important for this medical doctor to actually get the information. How does it work? how is the model work under the hood to understand it, why the model took this kind of prediction or not. So obviously there are regulatory agencies, FDA, for example, or any kind of fintech regulatory agencies. They need to know how does it work. I mentioned FDA regarding our solution. Yes, because not everything can be used by FDA, but I will come back to it in a minute during the samples. So obviously the managers, executive board members, we would like to convince some of the people in the board about the methods that we use, especially the results and how does it work. So data scientists, obviously, for debugging, for getting to know what's under the hood, how does it work, how does it process the input data, and obviously the users affected by the model. So let's imagine you have our credit scoring method. It's important to know how it works, especially if you would like to explain the customer why the customer is able to get a credit or not. So there are many methods how to explain. So obviously the first one, the most popular one, I think. No, maybe the second one is more popular, but text explanation. So explain the model using some text, some equations, formulas. It's easy, but obviously the text explanation doesn't give you the full understanding, especially if you use some equations. It's very hard to explain it to someone that is non-technical. Well, if you use a linear regression equation, it's easy, but if it's something more difficult, then it would be hard. So visual explanation is one of the most popular. So saying, okay, this is the graph, this is the chart, this is, I don't know, the heat map. That's something that we can visual, and visual is easy to be interpreted by also non-technical people. So the local explanation, if we are not able to explain the whole model, we try to find a part of the model and try to explain just this small part of the model. And maybe we are able to find more of such local explanation in this model to better understand what's actually going on in it. So explanation by example, that's another case where you cannot explain exactly the model, but you can actually take one example as an input and go through and try to explain what's going on if you go through the input data by the end. Some models are too complex, so you try to build a simplified version of this model and try to explain it by using this simplification, this simple model. And obviously feature relevance explanation, that's related to the data, and that's something that probably most of you use on daily basis. So a demo, short demo. Let me just open it. Here we go. So we have black box and white box methods. Here we go. Let me start with the black box one. Okay, that's a black box method. It's a black box. It's a really simple neural network with just 3 layers here. So 3 dense layers. The last one is actually on it's a softmax layer. So with a softmax evaluation function layer, and in this case we actually achieved 98% of accuracy, which is high. That's obviously on this data set. So it's just a typical example, but let's imagine, okay, how to explain what's going on in it. So it's really if we print the weights that we just trained from one of the layer, let's say that this is the second layer, then the weights that we have here, there are so many of such weights, and obviously the deeper the network is, the more layers we have and the more weights we have that are trained. It's even harder to explain. So that's a black box. That's a black box method, because we put some data and get a prediction, but we don't really know what's happening in it. So that's something that is hard to explain, even we have just only 3 layers. There are also white box methods, and they are plenty of white box method. This is one example. Decision tree classifier. Doesn't matter if we use C4.5, ID3, card, or any other implementation of the decision tree. Something that is easy to interpret, because we can draw it as a tree here. You can see, and even if the person is non-technical, we can easily transfer the x2, x1, and so on, x3 into into features, into explanation, what's x1, x2, and even if the non-technical person obviously doesn't know what's the Gini index, we don't need to know that to understand, because we can actually move this tree into a set of if rules, right? If this, then this, and so on. So it's easy to understand. So that's a white box method. There are plenty of white box methods, especially if you use scikit-learn. Scikit-learn is you know about it probably. It's a library with shallow methods, mostly shallow methods, and most of the methods actually are explainable. Okay. I mean, I have more methods here to go through, but I'm limited on time. So what's the process of an explainable AI project? So first of all, you need to understand the data that is coming that you are using. So you have structured data, unstructured data, different kind of graphs, CSV files, or unstructured like text, sound, or videos. Let me show you two examples on Titanic and melanoma. So melanoma is the skin cancer. Hold on a second, let me just open it. Here we go. That's a Titanic. Most of you know the Titanic challenge dataset from Kaggle. What I want to show you here is that we have some features here in the dataset. So first of all, it's about understanding, and it's a good example to understand what kind of features are really important for us. So obviously, some of the features like the name or the cabin, for example, or ticket, it's just something that we should remove, because it's a string and it's hard to use. I mean, at least at the first run. So we can drop it, and finally we can use a linear logistic regression to check the prediction. 78%, not so bad. But we can also check the feature importance here. Feature importance, obviously, the higher value, I mean, the closer to zero, the relevance is because we check it to the class here. So the higher value, the closer value to zero is the worse importance, and the closer to -1 or 1 is the better result. So you can see that actually the male and the class are the highest. So I mean the male, female, male, because it's a binary feature, and the class. These two are the most important, which is actually something logically, especially if you saw the movie The Titanic. But what can we actually get from the data more? So we can take the name, ticket, and cabin and take a look. Okay, what's more that we can do? So here's actually the name. So we go through, check 10 samples here, do lowercase and split it. So it's not really tokenization. It's just split. The Python split method, and take a look what kind of names we have. If we count it, we see that Mr. and Miss are the most popular. We have also a title like master. And if we take a look on the 4 and add it to the feature to our feature space, that's something that might be also something that we can count on, or might have this feature can be important for the prediction. So let's take a look at the ticket. We can do the same with the ticket. So we have different kind of words on the tickets that we can take a look. And the most important, I think, is the cabin, because as you know, that the iceberg actually crashed in a specific part of the ship, and some cabins could be more affected than the other ones. So we can check the letter here, A, B, C. It's like probably it's like in the airplane, like like the rows, not the rows, like the if you are by the window or not, then probably that's the number. So if we move it, we see that we have some of the letters here, and if we add it here, do the same logistic regression, we see, okay, we achieve a higher accuracy, obviously, and we check, okay, not only the female or male is actually important, you can see also that some other features here are important too, or like here is also important, or also the cabin, right? You see that actually the E-cabin, that's something that probably was also important when it comes to location of the passenger. All right, so that's one example when it comes to the Titanic, to understand the data, to actually start to explain what kind of data you can use. So when it comes to the skin cancer, so first of all, obviously we removed just the border. This is a very short example and very not too well. We didn't use actually machine learning here. This is just pre-processing, image processing. So we check the asymmetry, because this is one of the factor of if this mole here is a cancer or not. So what we did, we actually compared the histograms. Okay, so take the factors, and the closer to 1, the more symmetric it is. So closer to 0 means, okay, it's more like a skin cancer, right? You can see also in this image, okay, doesn't look so bad, right? In this case, that's for this image, it's not so bad really. If you look on it as a medical doctor, you see, that's not a cancer. This here, it might be a cancer. So the values are a bit lower if you compare it to these ones. But I will show you also another example. So here's the border shapeness that actually we checked. You can check it in our one of the article that I showed you a link on the first slide. We checked the fractal dimension to check the border shapeness, or the blue veil. You see here, that's something that's advanced cancer on this image. So what we did here also, we also used the histogram to check how many, how does it look like, right? And compare it to check the with different kind of RGB, HSV, and so on, different kind of color models. And this is how we checked just very simple cases, very simple patterns, like this is actually a pattern. The border sharpness, asymmetry is also something that it's a pattern. Together, when it comes to melanoma, you have more than 30 different patterns. We are now able to find 16 different patterns. So then, going to one comment to the melanoma case. Now we have about 16 different arguments about patterns. So you might ask, okay, why don't we use a binary classifier to classify the melanoma case? Many companies, or many projects that are available online now, where actually they achieve really good results on the binary classification, but that's not how you can explain, in many cases, how you can explain how the method actually works, because most of the projects actually use some deep learning models that are not really easy to explain explain for the doctor why it's actually classified as a cancer or not. So we actually moved to a solution based on patterns. So the second thing about the data, after the data, is about what kind of method you should use. And obviously you can use AutoML, you can use shallow methods. You can use different kind of solution, like AutoML, AutoScikit, AutoKeras, and so on, to find out what kind of model is the one that fits best for you. Okay, one more demo, and in one of the research, one that actually is presented in the article that I showed you before, we used, for example, a simple SVM classifier that is easily to explain. Here's just a few examples. A linear regression, that's something that even if it's not really explainable in 2 dimensions, like here, right? If you try to build a linear regression model, it's not really useful in this case. But if we move it to 3 dimensions, then it's easy to implement, to find out and explain it, to actually plot it like this one. Similar with the logistic regression, like here. So logistic regression here, hard to do it in 2 dimensions, right? Make it properly, but in 3 dimensions it's easy, and you can plot it. So these 2 methods and many other ones are easy to explain, like the bias classifier, for example. That's also very easy to, because it's a set of rules here of probabilities that you can actually do, and similar like decision trees. Or SVM, for example, that is also something that you can move to just a discrimination function. That finally, here's an example on the fraud detection. I will share with you also the notebook, so you can easily go through. So these actually are explainable. What about the deep learning methods? It's not so easy to interpret deep learning methods, because we have many layers, we have many weights. But there are some methods to actually explain it quite in an easy way, I would say. For example, here's an example of ImageNet that we use as a convolution neural network and implementation. And here's the dog that was classified as a golden retriever. This method is called the class activation mapping, and we are building a heat map to find out which regions of the image actually are important for classifying this image as a golden retriever. So you see the head, the ear, the nose a bit, maybe here the chest, and so on. And if you get another image like a cat or a car, then the heat map will be totally different. But it's something that is already that's something that you can use to explain, for example, for the FDA. There is a company called PhotoFinder. It's a German company that is producing the tools, the devices for the doctors to find out the skin cancer, and they use convolution neural network to explain the method. And what is more, they got approved. So they got approved by the FDA. So they now, if you are a medical doctor and you use the photo finder tool, then you use some machine learning methods in the back. Not ours. We are working with some other company to bring the machine learning part into the skin cancer diagnosis. So there are several, apart from the methods that I showed you in the notebooks, there are several tools. The LE5 is one of the most popular to explain the methods that actually we think might be black box methods. For example, XGBoost, it's an ensemble method, so it's not so easy to let's say if you have a random forest, that's a method that is not so easy to explain, because you're using many decision trees. So it's not so easy to explain because it's just too complex. But using some of the libraries, it's easy to explain it. Here are the open source libraries that are available, like 85, the Xi, for example, library as well. The IBM has also one. There are different kind of methods, like the SHAP, for example, method. That is here. You have a library. I have also a notebook on that, so I will share with you. And even if you want, I can also explain it on the next webinar. Old Lime, which is very popular for neural networks. Especially deep neural networks. You have scatter TensorBoard. Well, TensorBoard is not really an explainable AI solution. It's something that helps you to understand what the model, like here in the graph, that's not really explainable AI. It's more like going through and understanding, but it's I wouldn't consider it really as a fully explainable AI solution. Okay. Okay, so 2 more things. Just one, if you want to learn more, I will share with you the notebooks. also not only the one that I showed you today. I have more than 10 notebooks just on explainable AI, different methods. If you want to learn more about what I'm doing, you can meet us tomorrow on a different webinar, automated NLP-based question answering for the corona cases, and also machine learning failures on Wednesday. Whew. I think I'm in time. So any questions?
Okay, first of all, thank you. Thank you for your talk. Yeah, there are a few questions. So you in the beginning talked about image data. The question is, does it also work for text data?
Yes, yes, you can also use it for NLP. For example, you have some libraries that are dedicated also for, not maybe dedicated, but they can be used with some NLP methods like the scatter, for example, or there was one more, which one was it? Yeah, LE5, right? These can be used also with the NLP models, yes.
Okay. Another related question, anything done in the context of recommendations? So explainable recommendations?
We haven't done it yet. Most of our cases that we have done are related actually to health tech or fintech. We work together with a hedge fund with a headquarters in New York, that we are also using some explainable AI methods for fintech, also from some banking companies. Why only mostly health tech and fintech? Because these two industries are regulated and they need to use explainable AI. They cannot use just a model. They need to explain what's going on in there.
A related question, do you have any resources for explainable AI in the context of finance?
Yes, I can share with you. Just drop me an email, or maybe I can share it with the organizers, and maybe the organizers can share with you, or if you drop me an email directly, I can also share with you more about it. There is even one book about it that I can share with you. Yeah, I have it to print up. I have a printed version, but I can share you also the title later.
Here's my email. Would be great if you would share it with the organizers, then we can share it with the community. Sure. Another interesting question is, can this be used to help or to fight overfitting?
Well, to help or to fight overfitting, you can think about explainable AI as something that's kind of a debugging tool as well. But there are also other methods that are not really explainable AI methods to find an overfit. So you can obviously use some of the methods to understand and try to find the overfitting place where it's actually overfitting. But there are also simpler methods to do it.
Okay. An interesting question was, what are the evaluation metrics for explainable AI? So how do you probe the quality, assess the quality of your explanations?
Well, there are a few things. It's not you cannot really use, I mean, first of all, you can use the typical quality metrics like the, I don't know, sensitivity, specificity, and so on. But when it comes to specifically explainable, that's a bit more tricky, because how you can, if you go, for example, to the CAM method on the CNN, to compare and be able to explain it to someone. If someone non-technical is able to understand that, then it's good enough. But there is not one method actually to find, okay, if it's really explainable. Feature importance, for example, that's also something that is and helps you on explaining it like a quality metric. But there is no one really method, for example, for images to say, okay, that's good enough. You can still use the classic quality metrics for that.
Thank you.
But it's evolving. I mean, yeah.
Okay, thank you. One final question. You briefly touched upon the fractal dimension for detecting skin cancer. What dimension? What was it? Was it a boundary, or what did you consider and determine the fractal dimension of? And was there a threshold that would decide this is cancer, this is not cancer?
We didn't use, as I mentioned, we didn't use a binary classifier. So, I mean, we used binary classifiers for different patterns. And obviously the threshold, for example, for the border, so we used, we just calculated fractal dimension and use it in a SVM classifier. And we found just that, oh, it's really, we are able to distinguish. And we know exactly, because we have all of the images that we have in our database are marked by the medical doctors. That's asymmetry, that's border sharpness on this level, and so on. So we can compare it to the label, obviously, not only to the label like melanoma or not melanoma, because we are working together with the dermatologists. So they are able to explain us from a medical point of view how they would do it. Obviously, many of the guys, like medical doctors, the dermatologists, they will tell you, okay, I do it with an intuition, right? I just diagnose based on my intuition. But it's like, I'm not sure if you know Jeffrey Hinton, right? It's also something about explainable AI that he said that if you ask the model to explain their decision, well, you're forcing them to make a story. So also the people that are actually based on the intuition, but also the models, they need to try to find something to explain it, and that's the tricky part of the explainable AI.
Okay, Carol, thank you very much for your talk. Helena, Garcia, Tanush, very much. Thank you very much for your talks. Let me hand over the mic to Abhishek.
Oh, okay.
Do you hear me, Abhishek?
Yeah, I can hear you. Thank you very much to all the speakers. Amazing talks. And I hope all of you are staying home and being safe. So with this, we would like to end this meetup.
Thank you, everyone.
Yeah, with this, we would like to end this meetup and see you guys next time. Bye.
Bye bye. Thank you.